Today we're talking about blackbody radiation. It says the radius of our sun is 6.96 times 10 to the 8th meters, and its total power output is 3.85 times 10 to the 26 watts. Assuming the sun's surface emits as a blackbody, calculate its surface temperature in Kelvin using the result of part A, find the wavelength max. So we're going to use these equations down here, and you got the Stefan-Boltzmann Constant, and the symbol for that is this little thing right here, and it's called sigma. Okay, and you've got your power equation, which equals sigma times A, and that's going to be for the surface area, times E, which is emissivity, and that is just going to be, since we're using, we are assuming that it is a black body, so we're going to be using 1 for that, times T to the 4th. So let's write this out. So we've got P equals sigma times A times E times T to the 4th. Okay, so we can rewrite this because what we need to find is T. And so we can rewrite this as P divided by sigma times A, the area, and we can just leave that little E alone because I mean it's just 1. So equals T to the 4th power. Now we're not done yet because we need this T to be just a T, not T to the 4th. So how you can rewrite that is P over sigma times alpha, or A, the area, and that is going to be to the 1/4 power. Okay, and so and that's going to give us T. Now just some intuition on square roots and exponents and all that stuff. Let's say you had a number, let's just say xyz, and let's say you wanted to square root it. You can leave the square root on there, or you can signify that it's square rooted by putting 1/2, right? So if we were to square root it twice, you would just throw another 1/2 on there, which would give you 1/4. Okay. Likewise, so what we had was we had this T to the 4th. So we had this T to the 4th, and what we did was we square rooted it once, and that left us with T to the 2nd. We square rooted again, and that gave us T. And so you had to square root both sides over here twice, so which is 1/2 times 1/2, which gives you 1/4. Okay, so we've got P. That's just going to be the power output. We've got sigma, which is down here, and now we need to find the surface area. So surface area is going to be, you're just going to use the equation for surface area of a sphere, which is 4 times pi times the radius squared. Okay, so remember that the radius, of course, is just from here to here. Okay, and that is, so this number right here is going to be right here. Alright, so I think it's time to, and we can actually just do this all in one function on the calculator, so let's get our calculator out. Alright, so we've got P, which is 3.85 times 10 to the 26th power, right? And we are going to divide that by sigma, or the Stefan-Boltzmann constant, which is 5.6696 times 10 to the negative 8th. And then we need the surface area. Okay. So we've got 4 times pi, which is 3.1416 pi times the radius squared. So the radius is 6.96 times 10 to the 8th power, and that is in meters. And we are going to square that. And then we're going to take this whole function, remember, because this whole function is to the 1/4 power. So we've got 1/4. Alright, let's see what we get. Perfect. 5779.23. Okay. So when we do this, we get 579 Kelvin. So, and when you look at this, well, I mean, just by determining that, you can figure out kind of, it's going to be in here, so you know that your, if you were to look down here, the wavelength is actually going to probably be right around this 500 mark. Okay, so, but for the first part, here we go, 5, so that is how hot it is on the surface of the sun, and that is really, really hot. Alright, so let's do part B. For part B, we are going to be using the Wein's displacement law, and you've got your wavelength max times your temperature, and it's going to give you that. So we need to find the wavelength max. So you just take your wavelength max is going to be 0.2898 times 10 to the negative 2 divided by our temperature, 5779. Okay. So we take 5779, and then we take this 0.2898 times 10 to the negative 2, and that gives us 501 nanometers, because it's negative 7th and nanometers is negative 9th, so you throw that over 2 places and we get 501. Alright, so the wavelength max equals 501 nanometers. And if you look over here on the chart, so here's 400, here's 600, you got 500 in the middle, and if you were to see where that correlates, you would go up, and here's 5,000, and here's 6,000, and so it's going to be somewhere in the middle, which, or like right in here, which would actually be this. And that's how you solve that kind of problem.